All right, so this video is going to be about some of the properties of matrices, and there was a theorem in our textbook that I think is important to go over. It does not matter the order in which you multiply as long as the list remains consistent. What do I mean by that? You'll see here in the example that we don't have the commutative property of multiplication. Okay, so in normal integers, 4 times 2 is the same as 2 times 4, right? That's the commutative property. We don't have that in matrix multiplication. And again, we'll see that here. However, you can regroup, like if you had 2 times 3 times 4, you can say the associative property is okay. So you can say like 2 times 3, then times 4, that's the same as saying 2 times 3 times 4, okay? That works, but this one does not work in matrix multiplication. You can distribute to the left, that's fine. You can distribute to the right. Notice how we distribute to the right here. If you have a scalar, it is okay to have it outside. The scalar can be multiplied by A, it can be multiplied by B, and those are all the same as long as A and B stay in the exact same spots. And then we do have I here. I is the identity matrix. And I want to make sure you have in your notes that identity matrix means that you have ones on the diagonal, whatever it might be, okay? And then everything else is 0. And what the identity matrix does is when you multiply it by A, it ends up just giving it back to itself. This is going to be very important that we use later. All right, so let's go ahead and look at this. Like, why do we not have matrix multiplication that is commutative? Well, if I take A times B, let's see what the resulting 2 by 2 matrix would be. So I'd have 5 times 2, 10, 1 times 4, 4, 5 times 0, 0, 3, 3 times 2, 6, plus negative 2 times 4, negative 8, 3 times 0, 0, negative 6. Okay, so my resulting matrix, let me get rid of this over here. Give me some space. Okay, so my resulting matrix is 14, 3, negative 2, negative 6, and that's AB. All right, so let's do BA. All right, 2 times 5, 10 plus 0 right away, already out. Like, they're not going to be the same. Okay, so that is why we don't have the commutative property of multiplication. I have found a counterexample, cannot be true. So the order in which we multiply does really, really matter. A couple other things about properties. This is a really short video here. If you end up having A to the K, you want to make sure you multiply A by itself K times. And as long as A is non-zero, and X is in a vector of real numbers, okay, then A to the KX is the result of multiplying on the left-hand side that vector X, okay, so A, K, and then this vector X that you would have. But you need to multiply those A's all on the left-hand side K times, okay? If K is 0, it does have the normal identity, that anything to the power of 0 is 1, so you would just have X. And you can say that A to the power of 0 is then the identity matrix. So anything to the power of 0 ends up giving you the identity matrix. All right, we do have one more vocab word to go over in order to conclude our video here, and that is transpose. What transpose means is take the columns and make them, or take the rows, excuse me, and make them the columns. So if I take, I guess it works both ways, but if I take the row AB, notice that's the column of the transpose. If you look at C, notice 1, 1, 1, 1, 1 is now the column of the transpose. If you transpose a transpose, you get back to the original matrix. If you take A plus B, and then transpose it. That's the same as taking each transpose and then just adding it. That's because the term by term pieces, the term by term pieces are going to end up matching up. Scalar multiplication works the same way that we might think about. Now, A times B and then transpose, you are going to end up switching. So you're going to do B transpose times A transpose. That's a really important piece to think about. Okay, so if I wanted to find AX transpose, let's go ahead and do that kind of piece by piece here. So AX is negative, or 1, negative 3, negative 2, 4, 5, 3. 5 minus 9 gives me negative 4. Negative 10 plus 12 gives me 2. And then I want to transpose that. So that's going to end up being a row vector instead. All right, let's take AX transpose and multiply it by A transpose. So X transpose is 5, 3, and let's go ahead and multiply that by A transpose, which is 1, negative 2, and then negative 3, 4. Okay, so if I multiply those together, I get 5 minus 9, so I get negative 4. And then I get negative 10 plus 12, so 2. And notice we just showed D here. Notice those are the same because AX transpose should be the same thing as X transpose times A transpose, and we showed that they ended up being the same thing here. All right, let's take X and multiply by X transpose. So X times X transpose would be 5, 3 times 5, 3. Now that's the same as saying 5 times this vector, right? And then 3 times this other vector. If you go back to some of the other work that we've done here, and so let's go ahead and make this a big 2 by 2. And this, again, this is a 2 by 1 times a 1 by 2, so we're going to end up getting a 2 by 2. So this first one's just going to be multiplied by 5. And then my second column vector is multiplied by 3. All right, let's do the opposite order. What happens when I take X transpose and multiply by X? So this is a 1 by 2, and I'm multiplying this by a 2 by 1. And so notice here, I'm actually only going to get a 1 by 1. I'm going to take 25 plus 9, and I just get a 1 by 1 vector of 34. All right, last question here. It says, is A transpose times X transpose going to be defined? Well, A transpose is a 2 by 2. And I'm multiplying that by X transpose, which X transpose is a 1 by 2. No, not defined.